Is time a river flowing forward at the same steady pace for everyone, everywhere? Does space stretch out like a vast, unchanging stage where the cosmic drama unfolds? Most of us live our lives assuming this is true. We set our clocks, measure our journeys. A minute for you is a minute for me. A meter here is a meter on the far side of the galaxy. But what if this deeply intuitive picture of reality, this solid ground beneath our feet, is just an illusion? What if time itself can stretch and shrink, and space can bend and warp like a sheet of rubber? This isn't just a flight of fancy, it's a question that has sparked one of the greatest intellectual adventures in human history. Our journey begins not with answers, but with a profound sense of curiosity. We look up at the night sky and see a tapestry of stars, planets, galaxies, all in motion. For centuries, we have tried to understand the rules that govern this celestial dance. We are pattern seekers, storytellers, cosmic detectives, driven by an insatiable need to know our place in the universe. To truly grasp the cosmos, we must be willing to let go of our most cherished assumptions, to question the very fabric of our perceived reality. The story of our universe is a tale told by two brilliant minds, each offering a radically different vision of the cosmos, one building upon the other, pushing the boundaries of what we thought was possible. This great debate pits two giants of science against each other. In one corner, we have Isaac Newton, the architect of a predictable mechanical universe, a cosmos running with the precision of a divine clock. In the other, Albert Einstein, the gentle revolutionary who shattered that clock and reimagined space and time as a dynamic interwoven fabric. Their epic duel of ideas wasn't fought with fists, but with mathematics and imagination. It's a contest that redefined gravity, reshaped our understanding of the universe, and continues to influence every aspect of our technological lives. So, who really won the right to define the universe? The answer is more beautiful and complex than a simple victory. Prepare yourself to travel through space-time. We'll start in a world of absolute certainty, where every cause has a predictable effect, a universe laid bare by the power of a single elegant set of laws. Then we will journey to the edge of reality, where gravity is so strong it can bend light, and time itself slows to a crawl. We will explore the strange and wonderful consequences of these two cosmic visions. By the end, you will see that our universe is far grander, far stranger, and far more magnificent than we ever dared to imagine. The cosmos is waiting. Let's begin the voyage and find out who holds the keys to reality. Imagine a universe created by a master clockmaker. A grand, intricate machine. Every gear, every spring, every pendulum moves with perfect, unwavering predictability. This was the universe according to Isaac Newton. He gave us a cosmos that was rational, orderly, and most importantly, knowable. In Newton's world, space was an absolute, unchanging, three-dimensional grid, a cosmic stage always there. Time, too, was absolute. It ticked forward at a constant rate for everything and everyone, from a falling apple to a distant star. It was the universe's unwavering heartbeat, the ultimate metronome for all motion. Newton's genius was to distill the complex motions of the heavens and the earth into a few simple, powerful laws. His first law tells us that an object will keep doing what it's doing, or staying still or moving in a straight line, unless something pushes or pulls it. It's the law of inertia, the universe's inherent laziness. His second law is the powerhouse. It connects force, mass, and acceleration. If you push something, it will speed up. The harder you push, the faster it accelerates. F equals ma, the bedrock of classical physics, letting us calculate a cannonball's trajectory with stunning precision. Then came his third law: for every action, there is an equal and opposite reaction. Rocket exhaust pushes down, the rocket goes up. Lean on a wall, the wall pushes back with the same force. These three laws described a universe of perfect balance and order. They suggested that knowing every particle's position and velocity at one moment would, in principle, let you predict the entire future and reconstruct the past. It was a deterministic vision, a cosmos stripped of mystery by human reason. The final piece was his law of universal gravitation. The same force pulls an apple from a tree, holds the moon in orbit around the earth, and keeps the planets in orbit around the sun. Gravity, an invisible string connecting every mass to every other. One of the most vexing problems was the orbit of Mercury. Newton's laws predicted the planet's path almost perfectly, but not quite. Mercury's elliptical orbit slowly rotates over time, a phenomenon known as precession. After accounting for the gravitational pull of all the other known planets, there was still a tiny unexplained discrepancy, a shift of just 43 arcseconds per century. Astronomers tried to explain it away by hypothesizing an unseen planet even closer to the Sun, which they called Vulcan. But search as they might, Vulcan was never found. Another crack appeared in the realm of light. The Scottish physicist James Clerk Maxwell had unified electricity and magnetism, showing that light was an electromagnetic wave. His equations predicted that the speed of light in a vacuum was a constant, approximately 300,000 kilometers per second. But a constant relative to what? According to Newton's mechanics, speeds should always be relative. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the ground would see the ball moving at 120. But light didn't seem to play by these rules. So into this world of subtle but profound confusion stepped a young, unassuming patent clerk from Bern, Switzerland. His name was Albert Einstein. He wasn't a tenured professor at a grand university. Instead, he was an outsider, a brilliant thinker who spent his days examining patent applications and, honestly, his nights reimagining the entire cosmos. In 1905, his miracle year, Einstein published a series of papers that would ignite a revolution in physics. He didn't just patch the cracks in Newton's model, he demolished the old foundation and built something entirely new and honestly breathtaking in its place. Einstein started not with gravity but with the paradox of light. He took the constancy of the speed of light as a fundamental principle of the universe. Then he asked a simple but profound question. What must be true about space and time for the speed of light to be the same for all observers? His conclusion was, well, radical. If the speed of light is absolute, then space and time must be relative. This was the core of his special theory of relativity. This theory also gave us the world's most famous equation, E equals mc squared. This tiny formula revealed a deep and astonishing connection between energy and mass. It basically states that mass is a highly concentrated form of energy and that a small amount of mass can be converted into a tremendous amount of energy. Special relativity was a monumental achievement, but Einstein knew his work was not yet complete. His theory dealt with constant motion, but it didn't include acceleration or, more importantly, gravity. With his general theory of relativity published in 1915, Einstein presented a new vision of gravity that was as beautiful as it was bizarre. He asked us to imagine space and time not as a rigid grid but as a single four-dimensional fabric, space-time. In the absence of matter and energy, this fabric is flat. But massive objects like planets and stars create dents or warps in it, kind of like a bowling ball placed on a trampoline. What we perceive as the force of gravity is simply the effect of objects following the curved paths created by these warps in space-time. The Earth isn't being pulled by the Sun. It's following the straightest possible path through the curved space-time created by the Sun's immense mass. This new picture of gravity explained phenomena that Newton's laws could not. Remember the strange wobble in Mercury's orbit? Einstein's theory predicted it perfectly. As Mercury orbits the Sun, it passes through the most deeply curved region of space-time in our solar system. This warping of space itself causes the planet's elliptical path to precess at exactly the rate that had been observed, 43 arcseconds per century. The long-standing mystery was solved not by an imaginary planet, but by a complete reimagining of the nature of gravity. Einstein's theory made another startling prediction. If gravity is the curvature of space-time, then it should bend not just the paths of planets but the path of light itself. In 1919, during a total solar eclipse, the astronomer Arthur Eddington set out to test this idea. He photographed the stars near the Sun's edge and compared their positions to photographs of the same stars taken when the Sun was elsewhere in the sky. The results were clear. The starlight passing near the Sun had been bent by its gravity, shifting the apparent positions of the stars in precise agreement with Einstein's calculations. Without Einstein, the global positioning system, that GPS that so many of us rely on every day, would not work. The GPS network consists of a constellation of satellites orbiting the Earth, each carrying a highly precise atomic clock. But here's the catch. Einstein's theories of relativity tell us those clocks in space are ticking at a different rate than our clocks on the ground. First, due to special relativity, the satellites are moving at about 14,000 kilometers per hour, which causes their clocks to tick slightly slower than stationary clocks on Earth by about 7 microseconds per day. But the second effect from general relativity is even larger. The satellites are in a weaker gravitational field than we are on the surface, so their clocks tick faster by about 45 microseconds per day. When you combine these two effects, the clocks on GPS satellites get ahead of clocks on Earth by about 38 microseconds every single day. It sounds tiny, but if engineers didn't correct for this, GPS navigation errors would accumulate at a rate of 10 kilometers per day. Beyond our daily commutes, general relativity opens a window into the most extreme and violent phenomena in the cosmos. It predicted the existence of black holes, objects so dense that their gravity warps space-time into a bottomless pit from which nothing can escape. For decades, they were purely theoretical, but today we have observed their effects throughout the universe. From the stellar mass black holes left behind by collapsed stars to the supermassive giants that lurk at the centers of most galaxies, including our own Milky Way. We've even taken a picture of one's shadow, a direct visual confirmation of Einstein's mind-bending theory. Furthermore, Einstein's theory predicted that when massive objects like black holes or neutron stars collide, they should send out ripples in the fabric of space-time itself, called gravitational waves. For a century, these waves were too faint to be detected. But in 2015, the LIGO Observatory made history by directly detecting gravitational waves from two merging black holes over 1 billion light-years away. This monumental discovery opened a completely new way to observe the universe, allowing us to listen to the cosmic symphony of colliding worlds. Einstein's revolution is not just a theory, it is a tool that allows us to see and hear the universe in ways Newton could never have dreamed of. So, in this grand cosmic showdown, who wins, Newton or Einstein? The beautiful answer is that they both do. The genius of Einstein's revolution was not that it proved Newton was wrong, but that it revealed the limits of his perspective. Newton's laws are not incorrect. They are an incredibly powerful and accurate approximation of a deeper reality. For the vast majority of human experiences, building a house, driving a car, launching a probe to Mars, Newton's physics is more than good enough. Think of it like a map. A flat map of your city is incredibly useful for getting around town. It's simple, easy to read, and perfectly adequate for its purpose. But if you try to use that same flat map to plan a flight from New York to Tokyo, you'll run into trouble because it doesn't account for the curvature of the Earth. You need a globe, a more complete model of reality, to get the long-distance journey right. Therefore, the question isn't about a winner and a loser, it's about choosing the right tool for the job. You wouldn't use a sledgehammer to fix a watch, and you wouldn't use a jeweler's screwdriver to break concrete. Newton gave us the physics of the everyday, the tangible world we can see and touch. He laid the foundation for classical mechanics and engineering, and Einstein gave us the physics of the extreme, the cosmic scale of black holes, the Big Bang, and the subtle warping of time itself. He provided the framework for modern cosmology. Each master reigns supreme in his own domain. The story of the universe, as told by Newton and Einstein, is a testament to the power of human curiosity. Newton gave us a predictable mechanical cosmos, a grand clockwork set in motion by universal laws. He taught us that the universe is knowable. Then Einstein came along, revealed that the clockwork itself is flexible. Space and time are dynamic players in the cosmic dance. He taught us the universe is far stranger and more wonderful than we had conceived. Together, their work forms the twin pillars of modern physics. It has allowed us to decode the secrets of the cosmos from the smallest particles to the largest structures. Yet for all their genius, their story is not the final chapter. The symphony of the cosmos is unfinished. Today's physicists are wrestling with questions neither could answer. Einstein's general relativity, our best theory of gravity and the large-scale universe, does not play well with quantum mechanics, our best theory of the very small. At the heart of a black hole or at the moment of the Big Bang, the two theories give nonsensical, contradictory answers. The universe is still hiding its deepest secret, a single unified theory. This quest for a theory of everything is the great challenge of 21st century physics. Scientists are exploring mind bending ideas like string theory, which posits that all particles are just tiny vibrating strings in higher dimensions, or loop quantum gravity, which suggests that space time itself is made of discrete, indivisible chunks. We are also confronted by mysteries like dark matter, the invisible substance that seems to hold galaxies together, and dark energy, the enigmatic force that is causing the expansion of the universe to accelerate. These discoveries show our current understanding accounts for only about 5% of what the universe is made of. The legacy of Newton and Einstein is a spirit of relentless inquiry. It's the courage to challenge assumptions and imagine new realities. Science is not a destination but a perpetual journey, a continuous dialogue with the universe. The cosmos has not yet given up all its secrets. There are new worlds to discover, new laws to uncover, and perhaps another young mind right now scribbling in a notebook